Hi everyone. Today we're going to begin our study of one sample inference with means. So we're going to start back over at sampling distributions. We're going to go through sampling distributions, confidence intervals, and hypothesis test, all for one sample means. You've done this all with proportions, so a lot of this should be familiar, but we're going to start back at the beginning and go through the basics so that we have a really strong understanding of sampling distributions when we're dealing with sample means. Let's get started. Hopefully you recall we talked about a sampling distribution before, and remember the key here is that a sampling distribution is actually a population. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size and from the same population. So what we're really talking about is if we took every possible sample from a population of, let's say, size 2, and we picked every possible sample of size 2 and we created a distribution of all the statistics, so really a population of statistics, that would be our sampling distribution. Let's consider the population of 5 fish in the pond. So this is going to be a pond with a population of 5 fish. The total amount of fish in the pond is going to be 5. And these are my fish. Their lengths in inches are 2, 7, 10, 11, and 14. We need to calculate the mean and standard deviation of this population of fish. So we're looking for the mean of all the fish and the standard deviation of all the fish. Take a moment to pause the video and use your TI Inspire under List and Spreadsheets to find the mean and standard deviation for this population. The mean of the population of 5 fish in the pond is 8.8 inches. The standard deviation is 4.0694. Now notice that we're using an annotation here. We have the mean of x, where x is the length of a fish in the pond, so a length of a randomly selected fish. So this is the mean length of all the fish, and this is the standard deviation of all the fish lengths. Now we're going to build a sampling distribution. We're going to take samples from this population. Let's take samples of size 2 from the population of fish. How many samples of size 2 are possible? If you'll recall from earlier this year, this is really a combination. The order doesn't matter to us. It doesn't matter whether I choose the fish with length 2 first or the fish with length 7 first, as long as I pick those 2 fish. So we're looking at a combination from the 5 fish in our population, selecting 2 at a time. So this is 5 factorial over 2 factorial times 5 minus 2, or 3 factorial. This comes out to a total of 10 possible samples of size 2 from the population. In other words, our population of all the possible samples of size 2 would contain 10 samples of size 2. So we're going to take a moment to write every one of the possible samples of size 2 in this chart. For example, we have pairs 2 and 7, then we have pairs 2 and 10. So take a minute to pause the video and continue when you've filled out the entire table. So we've got 2 and 7, 2 and 10, 2 and 11, 2 and 14. Remember, order doesn't matter here, so we're not going to repeat 2 and 7 with 7 and 2. Those 2 fish have already been selected. We've also got the pair of fish 7, 10, 7, 11, and 7, 14. Then we've also got 10 and 11, and 10 and 14, and finally fish 11 and 14 in length. So now we need to go through and we need to find the mean for each of these pairs. So we're going to find the x bar, or the sample mean, for each of the pair of fish. So for example, in this first pair right here with lengths of 7 and 2, that's a total of 9 divided by my 2 fish gives me a mean length of 4.5. So let's take a minute to fill out the rest of this chart by finding the x bar, or the sample mean, or the sample statistic for each of these pair of fish. When you're done, press play and come back and watch the rest of the video. Let's make sure we calculated all of the x bars, or the sample statistics or sample means, for each of the pair of fish correctly. Now we need to find the mean of the x bars. In other words, the average of all the sample means. So we need to average all of these sample statistics for all of our fish. We also are going to calculate the standard deviation for x bar. Notice we're using the symbol here for a population standard deviation. The reason for that is we have taken all of the possible samples of size 2 from our population, so we really have a population of samples of size 2. This is what we mean by a sampling distribution. When we take a sampling distribution, we're taking all the possible samples of size 2. So take a moment to find the mean of all of the sample statistics and the standard deviation of all of the x bars as well. You'll notice that the mean of x bar is 8.8 and the standard deviation of our x bars or our sample statistics is 2.4919. So notice that this correlates the mean of the actual population of all fish. Our mean for all of our fish lengths was also 8.8. So we notice that there's a relationship between the mean of our sampling distribution and the mean of our population of fish. Now, the standard deviations are not the same. The standard deviation for our population of fish happened to be 4.0694. This standard deviation for our sampling distribution for n equals size 2 is 2.4919. Take a moment to think about how the sampling the sampling distribution has a mean and standard deviation, and how does that relate to the population? Now let's repeat the procedure with a sample of size n equals 3. So we're also going to look at a sampling distribution for n, or the sample size of 3, meaning we're going to take all the samples of size 3 that are possible from our population of fish. Remember, those were fish that had lengths of 2, 7, 10, 11, and 14. We're going to pick all the possible samples, in other words, all the combinations from these 5 fish chosen 3 at a time. So again, this is 5 factorial over 3 factorial, and 5 minus 3 is 2 factorial. So this comes out to 5 factorial over 3 factorial times 2 factorial, or there are going to be 10 possible samples of size n equals 3 that we could pull from this population of fish. If each of the samples is going to be called a triple. So we could take the sample of fish 2, 7, and 10, and that would be our first triple. Pause the video, complete the rest of the table, finding all of the 10 triples of fish that we could get from this population. Now that we've got our population of samples of size n equals 3, or our population of triples from our population of fish, we need to find the x bar, or the sample mean for each of these triples. Now that we have all of the statistics, or all of our sample means for each of these triples, we need to find the mean of the sample means, or the mean of the x bars, and the standard deviation of the sample means, or the standard deviation of the x bars. So we're going to put these in our calculator under list and spreadsheets and calculate the mean and the standard deviation for all of these values. Remember, again, this is a population of all the samples of size 3, so we're calculating a population standard deviation, not a sample standard deviation. Pause the video, go find these numbers, and then come back to us when you've got the answers. Okay, so the mean of x bar, the mean of the sample means, is 8.8, and the standard deviation of the sample means happens to be 1.6613. So take a look at your notes. Compare the mean and standard deviation of the original population, the mean and standard deviation for the samples of size 2, for the sampling distribution of all the samples of size 2, and here are the mean and standard deviation for the sampling distribution for all the samples of size 3. Make sure you take a look at all 3 of those examples and write down what you notice. What do you notice about the mean of the sampling distribution compared to the mean of the population? And what do you notice the relationship is between the sample size and the standard deviation of the sampling distribution? If you notice that the mean of the sampling distribution equals the mean of the population, then you're totally right. The mean of the sample means is just equal to the true mean of the population. This is a very similar result to what we got when we looked at the mean of p hat. Remember, the mean of p hat, the sampling distribution for proportions, was just equal to p, which was the true population proportion. Here, the mean of my sample means of my x bars is just equal to the true mean of the population. You should have also recognized that as the sample size goes up, the standard deviation of the sampling distribution goes down. In other words, as n increases, my standard deviation for my sample means decreases. So the larger the sample size, the smaller the standard deviation. We say that a statistic used to estimate a parameter is unbiased if the mean of its sampling distribution is equal to the true value of the parameter being estimated. In other words, if the mean of x bar is equal to mu, the true mean of the population, then this statistic would be said to be unbiased. Remember when we talked about our jelly blubbers? When we first did the jelly blubber experiment in the first semester, the judgmental samples were centered way too high, and they were biased. When I asked you to pick jelly blubbers that you judged were best representative of all the population, we were all over the place. But when we randomly selected samples, the values of those randomly selected samples, when we plotted all of the possible samples that we took from students in our classes, we noticed that the mean of all of those samples were centered over the true mean. This is what we mean by an unbiased statistic. We have some general properties now that we need to discuss for sampling distributions for sample means. The first rule says that the mean of x bar, or my sample means, is just equal to the true mean of the population. For those of you taking AP Stats, this is on your formula chart. Our second rule says the mean of x bar is simply equal to the standard deviation of x bar is simply equal to the population standard deviation divided by the square root of n. Now, this rule only holds as long as no more than 5 or 10% of the population is included in the sample. Remember, if we have a finite population and our sample is too large, we can't use this second rule to approximate our standard deviation for our sampling distribution of x bars. So the examples that we did earlier when we were pulling samples of size 2 and 3, those were far too large of a sample from a very small finite population. If our population is infinite, then we don't have to worry about picking too large of a sample. But for a finite population, remember, we always want our sample to be no more than 10% of the population. Some books use 5. For us, we're going to say that we want our sample to be no more than 10% of the population so that we can use this approximation. Our third rule says that when the population distribution is normal, the sampling distribution of x bar is also normal. In other words, it doesn't matter what sample size we pick. If the population we're pulling from, the population of all of our data happens to be normal, then any sample of size n has a sampling distribution. So I graph all the samples of that size, and the sampling distribution of all those samples would also be normal. Now, what happens if it isn't normal? Let's take a look. We've got a sampling distribution applet that we can go to, and we can take a look at what's happening. In this applet, we're starting with, you see, a normal distribution. So we're actually going to animate a sample. So what we're going to do is we're going to actually pull a sample of 5 values from the normal population, and we're going to graph that blue box. That blue box is going to represent the sample mean, or the x bar, from the 5 pieces we took from that population. So if we do this again, we're taking 5 different x's and we're finding their sample mean. And we could estimate this again and again and again. Notice we're picking here for our blue boxes samples of n equals 5. So with a sample of size 5, if we were to do this again and again till we pick all the possible samples of size 5 from that population, then we could look at a sampling distribution for the sample means. Now, we're not going to be able to do all of it, so we're going to simulate it. We're going to take 10,000 samples of size 5 and we're going to plot those. So if we plot 10,000 samples of size 5, and we can even ask the applet to fit our normal curve, we've got a pretty good approximation. The reason is our population was normal. If the population is normal, then it doesn't matter my sample size. I could pick samples of size 5, and I'm still going to get a sampling distribution that is also normal, or that's well approximated by a normal. Now, if I don't start with a normal distribution, let's take a look at what happens there. So we're going to go through and let's pick a skewed distribution. So in this case, we've got a skewed right distribution. So again, we're just going to animate. We're going to pick 5 different possible x's from our skewed distribution, and we're going to graph the x bar, the sample mean from those 5. So we're going to do this again and again for samples of size 5. There's another sample of size 5, and this would take a long time, so we're going to speed this up by doing 10,000 samples at once. Now, if you notice, our normal approximation is not as good as it was before, because I'm not pulling samples of size 5 from a normal population. I'm pulling them from a skewed population. So let's actually clear all of this and let's increase our sample size. Let's take a look now at samples of size 25 and let's simulate a sampling distribution of size 25. This is a little more closely approximated by a normal distribution. One thing to really note here is our blue curve, our simulated sampling distribution, certainly has less variability and a smaller standard deviation than our original parent population. In fact, if you look at the data over here on the left, the red data for SD for the parent population, it has a standard deviation of 6.22 units. If I look at the blue graph, my simulated sampling distribution, the standard deviation there is 1.24. Remember we said as my sample size goes up, I'm actually going to be decreasing my standard deviation. All right, so let's go back to our notes and let's look at the last property that we're going to talk about for sampling distributions for means. Rule 4 is called the central limit theorem. The central limit theorem states that if our sample size n is sufficiently large, the sampling distribution of x bar is well approximated by a normal curve, even if the population is not itself normal. So really our only question here then is, what is sufficiently large? Well, we looked at the example on the applet and we saw when we were at a sample size of 25, it was certainly closer to normal than our sample of size n equals 5. For the central limit theorem to work, we're saying that it's sufficiently large if our sample size is at least 30. If we're picking samples of at least 30, and remembering that they cannot be more than 10% of our population, if we're picking samples of at least 30, then they're considered sufficiently large. Therefore, the sampling distribution of all of our x bars is going to be approximated by a normal curve. Well, we have to approximate by a normal curve to do any of the calculations we've been doing. So this is really going to become one of our assumptions if we're doing inference for means. So remember, one of our assumptions is always that we verify that we've got an approximately normal distribution. If the parent population is normal, the sampling distribution is automatically normal. If I don't know about the parent population, or even if I know it's skewed or uniform, I can assume the sampling distribution for x bar is approximated by a normal curve as long as my sample size is at least 30, based on the central limit theorem. All right, so let's put everything together now, and we're going to work some example problems. In our first example, we're looking at the Army. They report the distribution of head circumference among soldiers is approximately normal, with a mean of 22.8 inches and a standard deviation of 1.1 inches. So this is the mean for any individual soldier's head. On average, a soldier's head has an average circumference of 22.8 inches and a standard deviation of 1.1. We're going to calculate the probability that a single randomly selected soldier's head will have a circumference that's greater than 23.5 inches. Well, we said that this is approximately normal, so we can draw our approximate normal curve here. Remember, our normal curve is based on a mean and a standard deviation, with each normal curve being different. So this normal curve is centered at a mean of 22.8. And basically, every one of the dots that would make up this normal curve are individual soldiers' head lengths. And so the Army is literally plotting all of the circumference of the soldiers' heads over time. Our question is, what is the probability that X, a randomly selected soldier's head, will have a circumference that's greater than 23.5 inches? Remember, if we're finding the area under a normal curve, we're looking for a probability. 22.8 is the center, so 23.5 would be to the right, and we want to calculate the area above 23.5. So on your calculator, this is a normal CDF calculation. Our lower bound is 23.5. Our upper bound is something large, infinity. Our mean is the mean of the soldiers' heads, 22.8, and our standard deviation is 1.1 inches. So if we put this in our calculator, we find the probability that we randomly pick a soldier and that particular X, that particular soldier, has a head circumference greater than 23.5. We find the probability to be 0.2623, or in other words, 26.2% of the time, we will be able to randomly select a soldier who has this large of a head circumference. So let's take a look now at how that normal calculation, finding the value of a particular X in a normal distribution, differs for a sampling distribution. Now we're going to find the probability that a random sample of 5 soldiers will have an average head circumference that's greater than 23.5. What I'm really looking for now is what's the probability that X bar, a random sample, has a sample average or a sample mean that's greater than 23.5. So we had on the last slide, we had this nice normal curve that was centered at 22.8, and each of those dots represented an X, an actual soldier who had a calculated head circumference. What we're really saying now is, what if we picked 5 of these soldiers and we took those 5 soldiers and we found their X bar, their average head circumference. So we could find the average of those 5 soldiers and we could get an X bar or a sample mean. And we could repeat this for every possible sample of size 5, and we would have a sampling distribution for sample means. Remember, the mean of our X bars of our sample means is just equal to the true mean of our population, 22.8. Now, when we're dealing with a sample mean though, this curve has now got a mean of 22.8, but the standard deviation for my sample means is sigma divided by the square root of n. Or in this case, it's the sigma that we had for the previous problem, standard deviation of 1.1, divided by the square root of 5, because that was our sample size. So now we want to calculate the probability of finding an average that's greater than 23.5. Now, take a minute. Do you expect the probability we calculate to be more or less than we got in part A for this problem? Pause the video, jot down your ideas, and then press play when you're ready. The answer here we would expect the probability to be less than we got in part A. The reason is in part A we had a standard deviation of 1.1. In this question, when we're dealing with the sample means, the sampling distribution of sample means, my standard deviation here was 1.1. For my sample means, it's 1.1 divided by the square root of 5. So our standard deviation actually decreases, meaning more of my curve is near the center or near the mean value, so I'll have less tail area. So if I want to know the probability now of being greater than 23.5, this would be a smaller probability. So we can calculate the probability that X bar is greater than 23.5. Again, this is a normal CDF. My lower bound is 23.5. My upper bound is something very large. My mean of my X bars is just equal to the true mean from the population, which was 22.8, and my standard deviation is now 1.1 divided by the square root of 5. So if we use our calculator to find this answer, we will find that the probability of getting an average of 5 soldiers whose average head circumference is greater than 23.5 is going to be 0.0774. So it is much less likely to get an average head circumference that's an extreme value than it is to pick one randomly selected soldier that has an extreme value. All right, so you've got the notes. Take a minute to look through your notes and work the next problem. Press play when you're ready to go over the answer. In looking at this problem, we're actually looking at a team of biologists who are studying a children's fishing pond. X is going to represent the length of a single trout taken at random from the pond. We know that this has a normal distribution, so if the parent population is normal, the sampling distribution is automatically normal. We know it has a mean of 10.2, so on average, a trout has an average length of 10.2 inches and a standard deviation of 1.4. We want to know what is the probability that a single trout taken at random from the pond is between 8 and 12 inches long. So let's write our probability statement. This is the probability, not a mean, but a single trout, so 1x, is between 8 and 12 inches long. Well, remember we said that we have a normal distribution, so we have a normal distribution centered at 10.2. I want to know the probability that it is between 8 and 12 inches long. So we're looking at this area under our normal curve. So we can calculate the normal CDF. My lower bound is 8, my upper bound is 12, my mean of 10.2, and my standard deviation of 1.4. The probability that we randomly pick a trout from this pond and it is between a length of 8 and 12 inches long is 0.8427. or 84.3%. So it's highly likely that we would pick a random trout in this range. So let's compare that to the probability that the mean length of 5 trout taken at random is going to be between that range. So now I'm dealing with a mean length of 5 trout. So instead of having my original normal curve where each of the values was an actual trout, I'm going to be dealing with a sampling distribution of all the possible samples of size 5 taken from this population. Remember, my sampling distribution, in other words, my sampling distribution of sample means, shares the same center as the population. So in this case, that's a mean of 10.2 inches. But my standard deviation for X bar is actually smaller than the standard deviation for the population. It's my population standard deviation divided by the square root of 5. So now in this problem, we're wanting to know what's the probability that an average of 5 trout, so an X bar, is between 8 and 12 inches. Well, let's take a look at these curves. I want to know the probability that we're talking about between 8 and 12. So is it more or less likely now, am I going to have a higher or lower probability of being between 8 and 12? Well, if you think about what we're talking about here, I'm looking for values that are closer to the center. Remember, as my standard deviation goes down, more of my values are closer to the center of a curve, so I should get an area that's much larger. So let's calculate the actual area under this curve. So we're going to find the probability that an X bar is between 8 and 12 inches. This is a normal CDF. Again, my lower bound is 8, my upper bound is 12, my mean is 10.2, and my standard deviation is 1.4 divided by the square root of 5. So we will actually see that there is a higher probability of being within that 8 to 12 range for a sample of trout than for one single trout, because more of my values are close to the mean. So if we calculate this, we find that now there is a 0.997 or a 99.7% probability of finding an average of 5 trout that are between 8 and 12 inches long. All right, let's work backwards now. What sample mean would be at the 95th percentile? So I'm dealing with means, so I'm dealing with my sampling distribution for X bar. So I'm dealing with my population of sample mean. So remember, this is the curve now where every one of the values in the curve is a sample mean. I want to know what would be at the 95th percentile. Remember, the 95th percentile is the place where 95% of all values on the curve fall below that point. So if I want to know the area under a curve, I do a normal CDF. If I have an area under a curve and I want to go backwards and I want to find what x bar or sample mean gives me that, I use inverse norm. So we would say inverse norm here on our calculator. Your inverse norm calculation only does area below. Well, the 95th percentile says 95% of all values are at or below that sample mean. My mean of my x bars is 10.2, and since this is a sampling distribution, I'm using my sampling distribution standard deviation, or the standard deviation of x bar, which is 1.4 divided by the square root of 5. So if I do this calculation, I actually find that a sample mean equal to 11.2298 is at the 95th percentile, meaning 95% of all the samples I could take of size 5 of trout from this pond would have a sample mean of 11.2298 or lower. Let's look at soft drinks. We've got a soft drink bottler. They claim on average that cans contain 12 ounces of soda. That means our mean is 12 ounces for our population. X is going to be the actual volume of soda in a randomly selected can. X is normally distributed with a standard deviation of 0.16. So we can have a population that is normally distributed. We're going to select those 16 cans with a mean of 12.1 ounces calculated. What is the probability that the mean of the 16 cans, so that's my x bar, will exceed 12.1 ounces? So we're dealing with a sampling distribution for sample means. The mean of my sample means is just equal to the true mean of my population. Since the population was normal, the sampling distribution is also normal. I can calculate the standard deviation of this sampling distribution. It's sigma divided by the square root of n, or the square root of 16. So I can actually simplify my standard deviation for my sample means here comes out to 0.04. So we're going to calculate the probability of getting a mean, an x bar, that's at least 12.1. So when I'm asking you to calculate a probability of means, this is when you're dealing with a curve that is your sampling distribution of means. So if 12 is at the center, I'm looking for 12.1. I want to know the probability of getting that average for my 16 cans, or an average that's greater. So calculate this, press pause, calculate this, and come back and check. All right, so if you got 0.0062, you were correct. Remember that if I'm looking at my standard deviation, it's much smaller than the standard deviation for the population. So there is a lot less values, or a lot less probability of getting a sample mean at an extreme value. Let's take a look at one last question. Let's talk about hot dogs. A hot dog manufacturer is telling us that one of the brands of hot dogs has an average fat content of 18 grams per hot dog. All right, so this is going to be our mean of 18 grams per hot dog. And it has a standard deviation of 1 gram. Consumers would probably not be unhappy if the mean was less than 18 grams, but they would be unhappy if it exceeded 18 grams. An independent testing organization is asked to analyze a random sample of 36 hot dogs. So my sample size N is 36. Suppose the resulting sample mean is 18.4 grams. What is the probability that the sample mean is greater than 18.4 grams? So what I'm saying is, what's the probability that I went out and I got a sample mean that's 18.4 or higher from this particular curve? Well, remember, we're looking at a sampling distribution here. This is going to have a mean of 18 and a standard deviation of 1 divided by the square root of n. 1 divided by the square root of 36, or 1/6. So we're going to calculate the probability of getting a sample mean of 36 hot dogs that actually has an average mean value of 18.4 or greater. This comes out to 0.0082. So this actually should start ringing a bell to you. What I'm really saying here is, if the manufacturer was telling the truth and the mean really was 18 grams, then what's the probability of me getting something this extreme or more extreme if indeed the null is true? So we just calculated So we just calculated the probability that x bar is greater than 18.4, and when we did that, we got 0.0082. So remember, your p-value is the probability of getting what you got or something more extreme if the null is true. The null is that the manufacturer is really making hot dogs with 18 grams of fat. So what we're saying here is if the null was really true, is this evidence that the manufacturer is lying or that their claim is just false? Well, the p-value is the probability of getting this result if the null is true. Well, the probability of getting this result is 0.0082. In other words, I have a less than 1% chance of getting this result, and yet I got it. So the answer is yes. This result is not likely to happen by chance alone. So this does provide evidence that the manufacturer's claim is incorrect. So this should foreshadow a little bit of hypothesis testing that's coming back. Not today, but in the near future. Please go back and rewatch anything you don't understand. Come to class with a couple of questions. We'll answer those at the beginning of class, and we'll get to experience a flipped classroom where we work the actual questions in class next time. Bring your notes to class. See you soon.